Okay, thank you.
Thanks, Brant, for that technical introduction. So Brant's told you all some about the capabilities of our code, so now I get the chance to tell you some of the things that we're trying to do with it. And I titled this talk Resolving Realistic Galactic Outflows, but in the spirit of Roman's comment, I have retitled it Resolving More Realistic Galactic Outflows, because I am not claiming that I am doing all of the physics and that this is exactly true, but I would like to claim that I'm trying to do simulations that improve on previous work and therefore are more realistic in many ways. So I'm showing in the background an image that we've seen several times at this conference, especially today. It's M82, which is a nearby starbursting galaxy. And the reason I'm showing it is because it's a really fantastic image in which you can see a galactic wind that presumably is being pushed out of this galaxy as a result of the rapid star formation. And so this is one of the problems that my code is especially well equipped to deal with, because if you want to, in detail, calculate things like the structure and the density of the gas within these winds and the temperature of the different phases of the gas, you really need to have more or less constant resolution over a fairly large region in space. So in that sense, a static mesh code is really well suited to this type of problem. So just a little bit more about the kinds of problems that I'm trying to answer, in particular related to galactic winds. But what is the detailed structure of the turbulent ISM? So this is another problem where you really need constant high resolution over your gas clouds within your galaxy to get the highly dense regions, the structure of those correct. In addition, related to that is how does the stellar feedback from things like supernovae couple to the ISM, and then how is that going to be coupled to the galaxy on large scales through things like galactic winds? Again, having high resolution so that you can calculate the detailed structure is going to be really important, as we heard earlier, in terms of something like a supernova remnant. Unless you're really getting down to the scale in which these dense pockets of gas live, you're not going to be doing that calculation correctly. And of course, as I mentioned before, how are the galactic winds themselves structured? What is the mass and energy budget of gas of different densities and temperatures? So I got into this actually from looking into this fairly well-studied problem, at least numerically, which is the cloud shock interaction. So here I'm showing, just kind of a picture of what the initial conditions for a problem like this look like. You have some volume in which you place a cloud. In this case, you've got a cloud that's a sphere with constant density, and that's overdense with relation to the background, which it's in pressure equilibrium with. And then you're going to have a shock come into the computational domain. It will sweep over the cloud. It drives a shock through the cloud. Then the cloud will be sitting in a hot wind, and it's going to start to get ablated due to hydrodynamic instabilities, and eventually will mix in with the wind entirely. And so, as I said, this is well studied, but I will point out that almost all of the studies have done more or less this setup. Some of them have added much more physics, radiative cooling, magnetic fields, et cetera. But we're almost always talking about people looking at spheres, and spheres of more or less constant density. And so the questions people have been asking using this sort of problem are, how fast do you destroy the cloud? How fast is it broken apart? How fast does the high-density material mix in with the wind? In the context of triggered star formation, if you hit it with a shock as the material becomes overdense, are there regions that will collapse and form stars? As I mentioned earlier, the momentum injection to the ISM, this is relevant, as well as mass loading of galactic winds. Okay. So what did we do that was different? The analytic framework for this problem is going to become relevant, so I'm just briefly going to mention some of the important quantities. People tend to describe the evolution of these clouds in terms of a characteristic time scale, and that's called the cloud crushing time. So that's this TCC up here, and I'll show you in a minute why it's called that, but it just relates the cloud radius, the density contrast of the cloud with the background material, and the shock speed, And in general, you can describe things like how fast the cloud is destroyed in terms of some number of cloud crushing times, and that tends to remove some of the scale, physical scale factors from the problem, so you can relate it to small scale features or larger things like galactic winds. Okay, so what did we do that was different? In the more realistic context, what I meant by that is, of course, that there are very few areas, I think, in galaxy formation where you really have a constant density sphere of gas. Okay, right? I mean, on very small scales, the ISM is highly structured. The galactic winds that I've shown, I mean, none of them have giant blobs of constant density gas. That may not be true for some of the, simulations that we've seen, but I think it is fair to say that realistically, gas is much more highly structured than that. So we wanted to see what happens in this problem if instead of using a constant density sphere, you use a sphere that's excised from some turbulence simulation. In this case, it was a Mach 5 simulation. How does that change the result in terms of these various measurements that you can make? So this is a movie just showing, in two cases. I started with two clouds, each of which had the same mean density and the same total mass. But you can see that the evolution is very different for the constant density sphere versus this more realistic cloud that has a log normal density distribution. So the movie's going to play again in just a moment. The cloud crushing time scale occurs right about there. So that's when the cloud has been fully compressed. And you can see that while a spherical cloud tends to survive, and this is just the adiabatic case, for several cloud crushing times, you can see material that's of higher density than the ambient medium. The realistic cloud is destroyed much more quickly. And so clearly, if we were to put this in the analytic framework of a cloud crushing time scale, it doesn't match what people have shown for the spherical case, which is important because people use those time scales when they're trying to calculate, things like models of galactic winds. So this is just showing, snapshots from that simulation. We ran several of these simulations using different mean density clouds. And you can see that, exactly what I was just saying, as you move along in the simulation time, by the time you get to 3 or 4 cloud crushing times, in the spherical case, you've more or less completely destroyed the high density material in the log normal cloud. That said, we were able to put this into the sort of same analytic framework as the constant density case if, instead of using the mean density of the cloud, say, to calculate your cloud crushing time, you use the median density, which is perhaps, a more reasonable quantity given that that's, most of the volume of the cloud is filled with gas that's near the median density as opposed to the mean density. And so this is just a plot showing, these colors are showing 3 different densities of clouds that we tried, going from lowest density contrast in blue to the higher density contrast in red. And this is just showing the mixing rate, so how much mass was initially in the cloud, and by mass I mean high density material as compared to the background, and just how that falls off with time. And what you can see is that in our simulations, with each of these lines, we're doubling the density contrast. A sphere, a realistic cloud is going to get destroyed in more or less half the time that it would take a sphere of the same mass. Okay, so how am I relating this to galactic winds? This is work that's very much in progress, so I don't want anyone to quote me on any results. This is just kind of something that I'm playing around with right now. But doing those cloud calculations got me wondering what is actually the relevant feature in terms of how quickly dense material gets destroyed in these winds. This is relevant because people are trying to figure out right now how can we get cold dense gas at distant distances of several kiloparsecs, even out to hundreds of kiloparsecs from galaxies, given that a lot of these cloud calculations have shown that gas gets quickly heated and then mixed in and destroyed. So in an effort to sort of look at this in a different way, I thought, well, maybe the relevant quantity isn't the size of the cloud. It might be something like the column density of the gas. And so here I'm doing a similar calculation, but instead of spheres. I'm just putting slabs of turbulent gas. And then in this case, what I'm looking at is, how might radiative cooling affect this situation. And so this top movie is showing what you would get in the case where you don't have cooling, and the bottom movie is showing what you get in the case where you do have cooling. And what becomes readily apparent is that, in the case where you do have cooling, these very high density pockets of gas that you get in a turbulent distribution, they're able to maintain their shape, and they're able to stay at high density and not get shocked, and that's partly because the cooling is much more effective as it goes with the square of the density. So, like I said, this is ongoing work. I don't have any particular conclusions to put up, but the sorts of questions that we're trying to answer here: what are the mass loading? What's the energy budget of these different phases? We're trying to approach all of this using these very high-resolution simulations. And of course, given that my thesis is a code, there's always ongoing code work, and I'm happy to take any of your questions.
All right, a few questions.
So I guess I should start by saying this is incredibly impressive, this code you've got. 50 million GPU cores is unbelievable. But I see you have a point there on gravity. And so just doing hydro, it's of course local, twiddle your stencil if you're doing this. Do you think that you're still going to be able to get these kind of scalings once you have to add in all of the additional communication overhead that comes with doing gravity since it's non-local?
Yeah, so this brings up an interesting point that Brant did not have time to talk about, but we're doing all of the hydrodynamics on the GPU. That means we're doing nothing with the CPU. So given that hydrodynamics is often the more computationally intensive part of the problem, what we would like to do is actually do gravity perhaps on the CPU at the same time. So I don't know if we'll be able to maintain exactly the same scalings, but I have reason to believe that we'll do better than people that have to do both of those things with the same processor. So.
Yeah.
Yeah, so this is really interesting as well. I was just interested to know one of the main advantages of these Eulerian codes is leveraging adaptive mesh refinement, which doesn't particularly fit well with the architecture of the GPU. So do you ever see that getting a huge speed up on the GPU, or is it strictly for static meshes?
I don't have any current plans to investigate it. I think that, exactly what you said. I mean, right now, as far as I can tell, the major advantage comes from being able to do lots of floating point calculations correctly. So I'm more interested in adding things like MHD before I would get to the point of wanting to do an adaptive mesh.
So I'm wondering whether the cooling that you used was some simple function or a table, because I know that at the start of the talk on GPU, there was concern that if you work with a table or something data intensive, then you would run into a memory problem on the GPUs themselves if you try to do something like that.
Yeah, I think that's totally fair. So that was actually it was a relatively simple cooling function. We've implemented a couple of things, primordial cooling, as well as just more or less a fit to a solar metallicity cooling curve, which is what I was using there. I think that's entirely fair, and as I said, this is sort of ongoing work, partly because I haven't decided exactly what the best way to do the cooling is. I think if you're doing something simple, like just primordial cooling, it might be faster to just do it on the GPU, because it doesn't take that much time. But if we need to use something like cooling tables, then again, some mix of CPU and GPU might work out better.
All right, any further questions? Well, if not, thanks, Brant and Ivan again. And next speaker is